Welcome back, engineers. We have just initiated the next phase of our DSA series here on CSAI tutorial. Today, we are moving past basic string matching and entering the world of advanced string architectures. Our system status is online, and our primary optimization target is one thing: latency reduction. We're going to load the two high-powered modules today: Tries, our prefix networks, and rolling hashes, the math behind lightning-fast pattern recognition. If you have ever wondered how search engines suggest words as you are typing, or how researchers scan massive DNA strands for mutations, you're in the right place. Before we dive into the code, make sure to follow, hit that like button, and press the notification icon so that you don't miss any upcoming protocols in this series. Let's initiate the string manipulation sequence here. First, we must identify the enemy, the latency bottleneck. In a standard string searching, we often encounter an alert for O n by m complexity. This is what happens during a brute force search. Imagine the library problem. You're in a facility with millions of books, and you're looking for a specific phrase without an index. You're forced to scan every single spine, every single page, line by line. The cost is immense. For a document length n and a pattern length m, brute force is a total resource drain on your CPU. Our mission is to move away from that quadratic nightmare and reach an objective where we scale independently of the dataset size. We are targeting OL for lookups and O1 for updates. We want a search to feel instant, regardless of whether the haystack contains 10 words or 10 billion. Let's look at the first architecture, the Trie, also known as the prefix network. The core concept here is data atomization. In a standard list, we store whole words like apple or apply independently, wasting space on repeated characters. In a trie, we store shared pathways. Notice how app is a shared foundation. Both apple and apply branch off from that same central node. We aren't just storing strings, we are storing the journeys to create those strings. This structure is incredibly powerful because it allows us to perform prefix matching. If I search for app, I don't have to scan a list. I just follow the nodes. This sharing of memory for common prefixes is the secret sauce behind every high performance autocomplete system in existence. Now, how do we actually build these nodes? We have two primary blueprints. Option A is speed using a TrieNodeArray. Here, every node contains a fixed size array of 26 slots for lowercase letters. This gives us a O1 access to the next character, but it has a heavy memory footprint because many of those slots will remain empty. Option B is for efficiency, using a TrieNodeMap. Instead of an array, we use a dynamic hash map. This is the industry standard for Unicode or large character sets. You get O1 average access with significantly less wasted memory. When you're in a technical interview, choosing between these two demonstrates your senior engineer mindset. You're showing that you understand the trade-off between raw speed and memory conservation. If you want more interview prep content like this, check out the dedicated playlist on CSAI TTL. Let's walk through the insertion protocol. To add a word, we start at the root and iterate through every character. For each character, we ask, does a child node for this letter already exist? If the answer is no, we create a new node. If yes, we simply move into that existing child and repeat the process for the next character. Once we reach the end of the word, we flip a Boolean flag, is and or word equals true. This is vital because it allows us to distinguish between the words like car and cart when they share the same path. The complexity specs are beautiful. Time is OL, where L is the length of the word you are inserting. It doesn't matter how many millions of words are already in that try. Adding a new one only takes as many steps as there are letters in that word. Now that our data is stored, how do we retrieve it? The logic is search and start with is nearly identical until the very last step. We use a private helper function to traverse the path. For a whole word search, we must find the path and confirm the is end of the word flag is set. If we find the path for APP but the flag is false, the word doesn't exist. For prefix validation or starts with, we only care if the path exists. If we reach the end of the prefix without hitting a null pointer, we return true. Both operations are OL. This is why tries are the king of dictionary search. Their performance is completely independent of the size of the dictionary. Searching for cat takes 3 steps, whether your dictionary has 10 words or entire English language. Look at the performance graph. This is why we obsess over tries. The red line represents the standard search, where time grows linearly with the dataset size. As your data moves into the millions of words, that red line shoots toward the top of the grid. The green line is the try lookup. It stays almost perfectly flat because the complexity depends only on the length of the word L. Looking up CAT takes the same amount of time in a dictionary of 10 words as it does in a dictionary of 10 million. We have effectively decoupled our performance from the grid size. In the world of high-scale systems, this kind of architectural choice is what prevents servers from melting down during peak traffic. This is a recurring theme in our DSA series, finding ways to make the dataset size irrelevant. We have mastered prefixes, but now we have a new objective, pattern recognition. Sometimes we need to search a massive stream of data for a pattern that might appear anywhere, not just at the start. This is where the Rabin-Karp algorithm comes online. The problem with searching a haystack stream is that comparing string is a slow OL. If we scan character by character, we are back to that ON by M bottleneck. Our solution? Digital fingerprinting. We convert our pattern and our current search window into unique numerical signature called hashes. Comparing two integers in a single constant time operation for a CPU O1. Our strategy is to slide a window across the stream and only perform a real string comparison if the numerical signature match. It's like using a fingerprint scanner to identify people instead of checking their entire DNA sequence every time. How do we generate a signature that is unique enough to trust? We use the polynomial signature. The formula looks intimidating, but it's just a math. It's a summation of Si to the Pi, p raised to the power I mod m. We use a prime base, p, usually 31 for lowercase letters or 53 for ASCII, and we multiply each character by increasing power of that prime. This creates positional weighting. It ensures that ABC and BCA generate different fingerprints, even though they contain the same letters. Finally, we use a large prime modulo, like 10 raised to the power 9 plus 7. This is our safety net. It prevents the number from getting so huge that they cause a memory overflow while keeping the chance of two different strings having the same hash incredibly low. This is the aha moment of Rabin-Karp, the rolling hash. If we had to recalculate the whole polynomial every time the window moves, it would be no faster than a brute force search. But we don't recalculate, we update. Think of it like running a total on a receipt. When you remove one item and add another, you don't re-add the whole list. You subtract the old price and add the new one. In a rolling hash, we subtract the leading character, the outgoing signal. We shift the positional weights, which is multiplying the whole thing by p, and then finally we inject the new trailing character, which is the incoming signal. Because we are only doing basic arithmetic at the edges, the update happens in O1 constant time. We can slide across a billion character file and update our signature at every single step almost instantly. Let's look at the actual code for the update protocol. When we slide from index I to I plus 1, we perform this single line operation. First, we remove the contribution of the outgoing character, which is current hash minus text of at the position I into p pow. Then we shift the entire window to the left by multiplying by our base p. Finally, We add the new character entering the window. We wrap the whole thing in our modulo M to keep it clean. This is the peak of mathematical efficiency in string searching. We have turned a complex string comparison into a simple three-step math problem. This protocol is the engine behind many plagiarism detectors and forensic tools. If you're finding this deep dive has help useful, make sure to check out our other videos on CSAI TTL where we break down more math-heavy problems. In any hashing system, we have to talk about error correction because the pigeonhole principle, mapping an infinite number of possible strings to a finite set of integers, collisions are a mathematical certainty. If two different strings like AB and YZ accidentally produce the same hash, we call that a spurious hit. We handle this with two defensive protocols. Protocol A is verification. If the hashes match, we perform a quick manual character by character check. Protocol B is double hashing. We use two different set primes to generate two different hashes simultaneously. The probability of collision occurring in both hashes drop to a staggering 10 raised to the power minus 18. It's effectively zero. In an interview, always mention collision handling. It shows you are thinking about the edge cases that crash real-world system. Let's look at the spec sheet to see which tool you should deploy to your mission. The Trie, which is the navigator. It is your primary choice for prefix or dictionary searches. It has a high space complexity but offers incredibly fast deterministic OL lookups. It is best for autocomplete and IP routing. Rabin-Karp, which is our scanner, is a tool for pattern searching in a continuous stream. It uses almost no extra space, O1, and it is perfect for searching for multiple patterns at once by storing their hashes in a set. It is the champion of plagiarism detection and DNA analysis. If the problem involves prefixes, reach for the Trie. If the problem involves finding a needle in a haystack con- or contiguous substrings, reach for the Rabin-Karp. Understanding this tactical difference is what makes you a master of string algorithms. Where do these algorithms live in the real world? Let's look at that. Autocomplete system. Every time you type that something in a search bar, a Trie is traversing nodes to give you instant suggestions. IP routing. Routers use Tries to perform longest prefix matching to decide where to stand or your internal data packets. Plagiarism detection. Rabin-Karp scanned documents for long sequences of matching sentences to find copied work. Genomic sequencing. Scientists use rolling hashes to find repeated gene sequences across billions of base pairs. These aren't just academic exercises. They are the invisible gears that keep the modern world running. By learning these, you aren't just passing an interview. You're learning how to build global scale infrastructure. We are moving into the system standby now. Before we terminate the session, here are your pro tips for implementation. Prime selection. Use 31 for basic English or 53 if you're dealing with missed case ASCII. Modulo 10 raised to the power 9 plus 7 is your best friend to prevent overflow. Interview triggers. If you hear the word prefix, think Trie. If you hear sliding window or substring, think Rabin-Karp. Defense. Always, always mention collision handling to your interviewer. Session terminated. Upload is complete. Thank you for joining me for this deep dive. Comment below. What DSA topic would we tackle next? Do you want to see graph theory, dynamic programming, or maybe some system design? Let me know, and I'll see you in the next protocol. Happy coding.